We have one last concept in this chapter, and I'm going to start it by asking you this question. So please go ahead and read through and decide what you think the answer is. The correct answer is C. So if we imagine the south rim, some initial height, the bottom of the canyon, the river, some final, we know, even if we take a meandering path, which of course is what we would want to do if we're hiking, delta S would be along that path, but since the force of gravity acting on us, on a hiker, points straight down, and because work is force dotted with displacement, the dot product is accounting for the components that are parallel. The force of gravity only does work over the motion that is in the same direction, a delta y. Right? Gravity doesn't do any work over the components. I don't know how I keep doing that. I apologize. So gravity does not do any work over the horizontal components of the motion. We could consider this portion of the delta S as having an x component and a y component. The force of gravity does not do any work when the motion is horizontal because the force is perpendicular to the motion. It is not responsible or involved directly in speeding up or slowing down the hiker. But gravity does work over any vertical distance. So the work done by gravity, here we know it is positive simply because the force and the displacement are in the same direction. And then we say it is independent of the path taken because even if our path was steeper and we didn't meander so much, if the path had a larger angle of incline, the work done by gravity would still be equal to mg times delta y. It depends only on that vertical motion. Now, granted, the hiker is doing different amounts of work because that depends upon their force, which is along the path. But gravity itself does positive work as a hiker moves downwards. Now, if I write the work done by gravity as mg delta y, and we remember that delta y specifically means a y final minus a y initial. Y final is lower than y initial, so technically this is going to give us a negative answer. But the work done by gravity needs to be positive as a hiker descends. So I technically need a negative sign in this work done by gravity if I'm going to write it simply as mg times delta y. That way I get a positive answer when I have the negative value of delta y and the negative sign in the equation. I could write this out as the work of gravity is minus mg y final minus the negative mg y initial. Work done by gravity, technically we could say is always equal to this minus mg y final plus mg y initial. We call the work done by a force where this independence of the path taken, Work done by gravity here depends only on the vertical motion. So theoretically, hopefully this didn't happen to anyone, a person going straight down, free fall, the work done by gravity would be positive, and it would depend only on that vertical motion. Whenever the force that is acting, the work done by that force is independent of the path, we call that a conservative force. Any force whose work done depends only on the initial and final position is considered a conservative force. With conservative forces, we are going to be able to talk about these in terms of what we call potential energy. So this is leading us into chapter 10. Chapter 10 is going to replace this work done by gravity with potential energy terms. Potential energy meaning stored energy. Energy that is stored in the system because of its interaction, in the case of gravity, because of its interaction with the earth. That potential energy is just going to be another way of looking at the work. And so we're building up to what is called the conservation of energy equation, which some of you might be familiar with. If you're not, that's okay. I personally really like to use conservation of energy over the work kinetic energy theorem. And I will show you why. Ultimately, it doesn't matter which one we use. Fundamentally, they are the same thing. But that's where we're leading. If you happen to remember, the work done by a spring, when we integrated, we calculated it to be negative 1/2 ks final squared plus 1/2 ks initial squared. This implies or shows that only the final and initial compression or stretching of the spring matters in terms of how much work the spring does. If I have a mass on a spring and I watch this mass move to the right and then come back, the negative work as the spring slows the mass down cancels out with the positive work the spring does as it speeds the mass up. So overall, the work done by a spring is dependent only on initial and final stretching and compressing. Springs are considered conservative forces as well. So we will talk about potential energy of a spring. If we think about friction, the work done by friction as an object moves. So I have a box sliding along a surface. I know friction is opposite the motion. So I'm specifically talking kinetic friction. And so the work done by friction, it's always negative. So it's always removing energy from the system. The force of friction is constant. Delta S represents how far along the surface the friction acts and how far the box slides. This work is not independent of path. We say it is dependent on the path taken. This is a non-conservative force, which means we do not talk about it in terms of potential energy. We cannot talk about it in terms of potential energy. With friction, We know the surfaces, when we're talking kinetic friction, when one object slides on another. So even if you rub your hands together, rubbing your hands together makes them warmer. So we talk about the work done by friction as creating thermal energy. We're going to see this as a delta E thermal. And again, thermal energy specifically relates to some sort of change in temperature. The surfaces end up a little bit warmer than they were, so a bit higher of a temperature, and that thermal energy is what is created as friction is applied. So in chapter 10, which is now where we're moving, we're going to be looking at gravity, spring, thermal energy, these things in terms of multiple types of energy. And that will lead us to the conservation of energy equation, which in turn can also be used to represent conservation of energy, to relate forces and speeds and heights and springs all together and look at motion in that regard. That tends to be a favorite once you practice enough to get familiar with it. Most students generally like conservation of energy as a way to approach problems.